So we did this third problem we did. So next one is so it says so give a proof by induction for each of the following formulas. So the first part is 1 plus 2 plus 3 all the way up to n. So that is given by n into n plus 1 by 2. So do you know how the induction proof works?
No.
Okay. So let us check. Okay. So it has 2 or 3 steps. So first we do the base case. So the first base case is we see for a small value, the starting value of n. So here n starts from 1, right? So if n equals to 1, then the left hand side is nothing but 1, right? And the right hand side is 1 times 2 by 2. So that is also 1. So in this case, the result is true, right? Right. So the next step is the induction hypothesis. So here we assume that the result is true for n equals to k. For some k, the result is true. That is what we have is 1 plus 2 up to k into k plus 1 by 2. So we assume that the this is true, and the final step is inductive step. So we now prove that the result is true for the next one. So n equals to k plus 1. Okay. So that is the thing. So we'll use the help of the induction hypothesis to prove the next one. So here what you have to show. So you have to show that 1 plus 2k and then k plus 1. So this is, we have to show it is k plus 1 into k plus 2 by 2, right? So this is not yet done. This you have to show, right? So how to do it? So any idea how to prove it? So we know that this one is true. So using that, can we show the next one?
Maybe we can just replace 1 plus 2 plus k.
Right.
Can replace that below.
Yes. So what we will do is, so we start with the LHS. So we know the sum up to k. So that is k into k plus 1 by 2 and k plus 1. Right. So now if you simplify, what happens?
K squared plus k plus 2k plus 2.
Yes. So instead of multiplying, I can take k plus 1 common and then it will be k plus 2. Right. Right. So this comes our RHS. So this holds, right? So from here we can say that the result is true for any integer n. So this is the how the induction proofs work.
Okay.
and the result is true for. So n belongs to natural number or integer. So see the steps. So is it clear?
Yeah,
Right.
more or less.
Right. So let us try the next part. This one you can try, then we'll get more clarity. So part B is, so here same thing we have to prove by induction. So now instead of sum, we have sum of squares, 1 square, 2 square, 3 square up to n square. We have to show that that is equals to n into n plus 1 to n plus 1 by 6. Yes.
Yeah, I mean, we replace n by k, and then we have like the,
Right.
we
So
assume
what?
that is
No, we have
true.
to first verify the base step, right?
Okay, the base case with n equal to 1.
Right. So n equal to 1. The LHS is 1, right? 1 square.
1 square.
What is the RHS?
Well, plus 1 multiply 2 multiply 3 divided by 6 equal 1.
Right. So the base case is true. Then the inductive hypothesis. So it is true for
1.
n equals to k. Right. That is
K plus k plus 1 to k plus 1.
right. Now we have to
Then we prove
right
for
for n
n
equals to
equal to k plus 1. No?
yes. So how to do it?
1 square plus 2 square plus k2 square plus k plus 1 square.
Right. Then
In the other, I mean, we can just replace there.
yes, we can replace it.
We have k plus 1 to k plus 1.
Yes. After simplification, what will happen?
Maybe we can abstract k plus 1.
Right.
Would be k plus 1, k, so 2k plus 1 plus 6k plus 1 over 6.
Right. Then yes. Then I think we have to open up. Then again factorize, right?
Maybe we can try 2k squared plus 7k plus 7 plus 6, right? Okay.
Yes, plus 6. So what will be a factorization? 2k square plus k plus 7k, right?
Factorization. I don't remember how to factorize.
Yes, so we have to factorize, right? So here the product is 6 and 12. Sorry, 6 and 2. So that is 12, right? So we have to find something such that they add up to 7, right? So that is how we factorize, right?
Yeah, I remember some like a cross or something. Let's see.
So 7k we have, right? So that is the idea, right? So you have
It would
suppose
be like 1k plus 2 multiply 2k plus 3, something like that.
2k plus 3. Okay, sir. 2k plus 3 multiplied by
K plus 2.
k plus 2. Okay. Yes, I think that will come. So what are we doing is, so 2k square plus 7k plus 6. So that is 3k plus 4k, right?
Yeah.
So here actually we can take k, we get 2k plus 3, and plus 2 we take from the next one, right? So we have, right, so this actually matches with our formula, right? If I put k equals n equals to k plus 1, so it matches with our formula, right? So we can say that the result is true for any n.
Yeah.
By induction. Right. So next one is part C. So it's 1 plus a square all the way up to a power n. So this is given by the formula 1 minus a power n plus 1, 1 minus a. And the condition is that a is not equals to 1.
Right. The base would be n equal to 1.
Right. So n equals to 1, then the left hand side is 1. That is fine. What about the right hand side?
Then, but 2, 0, 2, 1. But if n is equal to 1,
Right.
that would be 1 plus a, right? Because
1. No. So the thing is, yes. So this is n equals to 0, right? It starts from.
okay,
Because,
0, yes, okay.
right. So that's why it is LHS is 1. Because if n equals to 1, then the LHS was also 1 plus a, right?
Yeah,
Right. So then
okay.
it will be 1 minus a divided by 1 minus a. That is also right. So this is fine, right?
Now, yeah.
Right. So then the inductive
Wait,
hypothesis. Yes.
n is 0. Yeah, that's fine, yes.
Right. So n equals to k, will assume it is true. So that is 1 plus a. So this is right. So now, so we'll now prove for.
N equal to k plus 1, right?
Right. So the left hand side will be right.
Yes.
So next step will be
We replace
okay.
1
So
minus 8 to k plus 1
yes. So if we simplify,
there.
what happens?
1 minus 8.
Yes. Plus.
K plus 1
Okay.
minus I k plus 2.
Right. So here these two things will cancel.
Yeah.
So here we have right. So this is so this matches with the formula, right? When n equals to k plus 1, so it matches with the formula, right?
Yeah. Yeah.
Right. Yes, the last one is slightly different. So let us see it. So here is C, right? Okay. This will also work out. So you have 1 times 2, then 2 times 3, 3 times 4, all the way up to, so n minus 1 times n, right?
Mm-hmm.
So n equals to, so equals to, you have to show it to n in n minus 1 by n. So what is the best step here?
N equal to 1.
No, n equal to 1 will not work, right? Because if you put n equal to
Mm-hmm.
1, then it becomes 0, right? 1 by 0 is not defined.
Then 2.
Right. So n equals to 2 is the best case here. So
Uh,
then the LHS is this thing. So that is half. And what is the RHS?
that would be 2 minus 1 over 2.
Right. So that is also half.
Yeah.
So this works. And then, so we assume that it is true for n equals to k. So k is bigger than 2 here because n is starting from 2. Right. So now,
Yeah.
so if we prove for n equals to k plus 1, yes, what will be the last sum? This one will be?
Plus k plus 1.
Right. So here the same idea. After this is same idea. So here if we replace this one,
Mm-hmm.
then what will be the simplification?
We can multiply k plus 1. That would be k squared minus 1
Right. Plus.
plus 1 plus 1. That would be k over k plus 1.
Right. So that will cancel out. Right. So this matches with our formula, right? So it's n minus 1 over n. So here n is k plus 1. So
Yeah. Yeah.
right. Okay. So this is fine. Okay. So next one is 5. So you remember the E zone that they have defined, right?
Yeah, they have a way of defining prime numbers.
Right. So E zone they have defined. So they are asked to describe all the E primes.
So you have like a field of E zone, which is 0, 2, 4, 6, 8, 10, minus 2, minus 4.
Okay.
And then
So
if you divide one with another, and if you find the divisor to be part of the field,
okay.
then you can say that is E divisible, right?
Yes.
If not, that will be E prime.
Okay. So E prime is so it cannot have, so usual thing. So prime is it cannot have other divisor than itself, right?
Mm-hmm.
Itself and the number 1, right?
Mm-hmm.
So yes, so other divisors it should be coming from that E set only. So it cannot be divisible by other numbers from the set, right? So yes, so how will you describe all the E primes?
But wait, so if you have, let's say, 6, 18, and 6,
Right.
they would be coprimes, right?
Okay, 1 minute. Let me go to that definition. Then it will be clear for you and we think we defined here, right? Yes. So 18, and you are saying?
Yeah, 18 and 3.
Okay. 18 is a E prime, right?
18 is an E prime.
Yes. Is it a E prime?
Uh, an even number P. An even number P is an E prime if it is not divisible by an even number. Yeah, because the divisor of 18 and 6 is not an E number, right? That's why
Yes. Yes. So
18 and 6.
18 is not divisible by 6. Yes.
That's why 18 is a 18 and 6 are E primes, right? Equal
Yes.
primes.
Yes. 18 and 6 are E prime. So what about 10?
Which one?
10.
14?
10. Where is 10 is a even E prime?
10, 10 also, I mean,
Right. Right.
it's another prime because
Right. Right. So 10 is also an E prime. So here actually all the list are E primes, right? So yes. So in general, how to tell? I mean, suppose you are given any number. So which is how will you decide whether it is an E prime or not?
so basically you divide, like if you have 18, I
Right.
guess you first find the factors of 18, right? Like
Okay.
2 and 3.
Okay.
And then all the factors must belong to the zone. If the factors that don't belong to the zone, that would be a
Uh,
prime.
okay. So for example, if I consider 28, right? So if I consider 28, so yeah, 28 is it a E prime or not?
28 is not a prime
Right. Why?
because 28 divided by 14, it is 2, and 2 is part of the zone. So
Right.
maybe you need to divide, like the number, you divide by all the numbers below that number, like 28, you
Right. So
divide,
28, we can write it as 2 times 14, where 2 and 14 both belongs to this E set, right?
uh
So it is not an E prime. So that yes, that is fine. So how?
yeah, so basically you divide by the lower numbers of that.
Okay. But I think that we can do it more simply. So we can just one categorization we can and say that it is whether a E prime or not.
Sorry?
Means we can categorize it more simply. So they are asking to find and to describe all the E primes, right? So what I'm saying is we can describe whether a number is E prime or not in just one line. Means we can just say it that if we do check this one, then you can directly say that whether a number is E
Okay.
prime or not.
Okay.
So yes, so the thing is only observation. What I am asking is, so from this list of numbers, what you can observe.
They are like they are like multiple of 4 plus 2 or minus 2.
No, none of them is a multiple of 4, right?
Yeah, but you add 2 or decrease 2.
Yes. So the thing is, what is happening is, so if anything is a multiple of 4, then it cannot be a E prime, right? Because okay, let me write now. Yes. So what is happening is, suppose you are taking any number n that belongs to this E zone, right? So if 4 divides n, right? So if 4 divides n, then I can write n as 4k, right, for some k.
Mm-hmm.
For some k, right? So this I can write it as 2 times 2k, right?
Right.
So then now both 2 and 2k, that belongs to the E zone, right?
Yeah. They are.
So then it is
They
no
cannot be
longer a
primes.
prime, right?
Yeah.
So the thing is, if the number is divisible by 4, then it is no longer a prime. So the thing is, if it is only divisible by 2 but not divisible by 4, then it will be an E prime. So that is the description. So the E primes are exactly those even integers n, for which n divided by 2 is odd. So if you divide by 2, it is an odd number.
Okay. If you divide by 2, it's an odd number. Okay.
So it is only divisible by 2 but not divisible by 4.
Okay. Okay.
Right. So the second part is part B. So they are saying that show that every even number can be factored as product of E primes.
Factor as a product of E primes.
Right. So this is the same idea, right? So we saw for our usual number system that it can be written as product of primes, right?
Mm-hmm.
So here just they are asking that it can be written as product of E primes.
Mm-hmm. Yeah, we use induction for this, right?
Yes, induction. No, I don't think induction will work.
Okay.
So because every integer is not inside in the set, right? So that's why induction also we have negative numbers. So induction only works for natural numbers.
Okay. Let's see. So can we use the assertion?
Yes, still can we?
I mean, we have the assertion, right? We have an assertion that says the number n can be factored into a product of primes in some way.
Okay,
Assertion 1.
right. So then how will you use that? So product of
Because we,
primes that include odd numbers. The primes other than 2 all are odd numbers, right?
sorry?
So a prime that is different than 2, right? All are odd numbers, right? Because 3, 5, 7 all are odd numbers, right?
Right.
So they does not belongs to the E set, right? So if we want to write it as a factor of product of E prime, then it first of all it must be an even number, right? Because e primes are even numbers, right?
Yeah.
So yes. So how will you write then?
So e primes are even numbers. Okay.
Right.
Yeah, but I mean, isn't that the same? Like, the assertion one will still work or not?
No, tell how it will work.
Mm-hmm. So in the demonstration, we say that if we have a number n,
Yes.
either n is is prime or n plus one is prime. One of those.
No. Why does it say n or n plus one? Both cannot. It can happen, right? Both of them are not prime, right?
But that's what we did in the demonstration. We said either n plus one is prime or n plus one is composite, and then we
Yes.
said that if n plus one is prime, there is nothing to do. But if it is composite, there could be a factorization.
Yes. Yes. So yes. Yes. So that is what I'm saying. So n we can start with n, right? So if we start with an n, then here is we are applying induction, right? But
Mm-hmm.
here actually we cannot apply induction because if n is there, then n plus 1 is not there, right? Because all are even numbers. So after 18, we don't have 19 in the list. We have directly 20. So this one you cannot apply, right? So that's what I told.
N plus two.
Yes.
I mean, we can just use n plus two.
Okay. So let me write down. So what we have is, so we start with any n. So we want to show that n belongs to E. So we want to show that n can be factored. So if n itself is an E prime, then we are done, right?
Right.
So right. So now if n is not an E prime, then what we have to do? So if not, then n we can write it as n1 times n2, right?
Right. You have two factors where
Right. For
n plus
some
one, n plus two are even numbers.
right. For some even numbers, n1 and n2, right?
Right. And then n1 could be also
Right.
another factorization.
Right. So n1 can be an E prime or n2 also can be an E prime. So and also both of them uh, may not be an E prime, right? So if n1 and oblique or n2 are E primes, so we leave them alone. And if not, we factor them again. Right. So like this, we can continue the process, right?
So
So
this is
this
like recursive, right?
yes, we can recursively continue the process, but the process has to stop somewhere, right? Because at each step, the number is getting smaller, right? So the thing is, we continue the process.
Yeah.
Right. But this process must stop since the factors are getting smaller.
I think there was like a property if
Yes, tell.
I don't remember exactly, but it was like if you multiply, if you have two numbers A and B,
Right.
and then like C divides A or C divides B,
Hmm.
the multiplication, when you multiply A and B, C also divides one of them or something like that.
Okay, let me write down what you're saying. So A and B are there. So C divides.
Uh, if C divides A
Okay,
or C divides B,
right.
then C will also be a divisor of A and B. A multiply B.
Yes, yes, that is true. That will be so. How do we apply here?
Let's see. Um, I don't remember.
So this will be not helpful here much, right?
Mm-hmm.
Right. So, but what we did that completes the thing, right? So at each step, we factor. So if it is an e prime, we keep like this. And suppose this one is not an e prime, then we will again factor
Mm-hmm.
out, and we'll check for the factors. If it is e prime, we keep it, and otherwise we continue this process. So this process will
Okay.
stop because at each step the factor size is getting reduced, right? So finally we will have the number as a product of e primes.
Yeah, but where did you stop when n or where n1 or n2 is equal to 2? That was the.
No, that may not be means we don't know because that will depend upon the number we are starting, right? So that may not be case that we reach at 2, right? So for example, we can construct an example to see how it is working. So we know that 18 is an e prime, right? And let us take
Mhm.
some bigger numbers. So what was the list? Any number you remember from the list of e primes? So e prime list is where is that? Yes, this one. So 18, 22, 26, right? So let us take that. Let us construct a number and see how it is working. So suppose we take the number n, 18, 22 and 26, right?
Mhm.
So yes. So suppose let us start with this number. So we know that this is the final factorization. So it may not contain 2, right? So our number is actually 10296, right?
Okay.
Right. So then what is happening? So if I start with this number, right? So then I can factor out 18, right? Right,
Right.
18 times. So it is 752, right? Sorry, 572. So now I know that 18 is a e prime because it is 2 times 9. So that we will not take, we will not further divide it. Now we are left with 72. Sorry, 572. And 572, I know it is product of 22 and 26, where each of
So
them are e
you're
prime.
so you're saying you will stop when you find the e primes factors.
Right, right. So when I get all the e primes, then you stop.
Ah, okay, 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 okay. So you don't touch anymore the 22, the 18 or 26. You don't touch it anymore because you
Because
already
all
found the
of the
primes.
because individually they are e primes, right? So we don't have to go further,
Yeah, exactly. Okay, 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 okay. Okay.
right?
Yeah.
So this is fine, right?
Mhm.
Okay. Part C, what they're asking is, uh, so part C they're asking that we saw that yes. So this one we already saw before that 180 that has 3 different prime factorization, right, in the set of E primes. So do you remember that?
No, I don't remember. Let's say 180. Okay. 180.
So one thing what I remember is it is 18 into 10, right?
Okay.
So 18 into 10 is a prime factorization. So similarly, I note 6 into something you can write. So 180 divided by 6 is 30.
30,
So this is also a E prime factorization, and one more is there. What is that? I think we did it.
12, no.
Yes, 2 into 90.
290, okay, yeah. 290, okay.
Right. So yes. So the thing is, what you have observed before, that the prime factorization in E zone, it is not unique, right?
So all of them are E primes. 18,
Right.
yeah.
So
All
we
of them
can
are E primes.
write as this. These are all product of E primes. So prime factorization in E prime means in E zone, that is not unique. But what they're asking is find the smallest number that has 2 different factorization as product of uh, E primes. So find the smallest number that has 2 different factorization. Yes.
The smallest number that has 2 different factorizations.
Yes.
The smallest number, like below 180.
Yes, yes, because 180, yes, I think it will be below 180 because 180 has 3 factorizations, right? So they are asking for 2 factorizations. So that has 2 different factorizations.
Okay, how would you do that? How 2 different factorizations?
Yes. So the thing is, yes. So we will get an idea from 180. So 180, what is the usual prime factorization? Can you tell me? So it is 2 times 2 times 45, right? So 45 is 3 times 15. So 3 times 3 times 5, right?
Okay, that's the factorization, okay, of
Right.
180.
So here, okay. So the smallest number is, first of all, it has to be divisible by 4, right? Because if we want two different factorization, it must be divisible by 4, right? Because it is not itself a E prime, right? So it has to be divisible by 4, right?
Because if it is divisible by 2, that would be prime.
Right. Then it will be an E prime, right?
We don't want it to be prime, E prime.
Right. So we want to have 2 different factorization. So what we can do is we can construct like this. So if I take 4PQ, right? So if we take where P and Q are prime, right? Means prime in the usual number system. Then we can write it as 2 times 2PQ, that is one factorization, and another I can write it as 2P times 2Q, right?
Mm-hmm.
So this will be the only 2 factorizations in as E prime factors, right?
But also can be 4 multiplying P and Q.
So P and Q are odd primes, right?
P and Q are odd because so basically all okay, so E prime numbers are those who, when divided by 2, are odd.
Right.
Okay. So PQ are odd numbers.
No, not odd numbers, odd prime.
Odd primes.
Right. So if I construct a number n such that it is of the form 4p times q, then it will have only these two factorization, right? Other factorization is not possible, right?
Sorry, what was the definition of odd prime? Because I got that it is prime. You divide by 2 and then you get an odd number. But odd prime,
Yes, odd prime. This is the usual thing, right? So the usual thing is in the usual number system. So that we have every number, every prime that is not 2, they are odd, right?
oh, so this is normal. This is not the ESON.
No. This is normal thing. So this is P and Q are coming from the usual primes. So 2, 3, 5,
So,
7. Yes. So we are not taking 2. So that's why I mentioned odd prime.
okay. Not 2. But okay, got it.
Yes. So if I
P
take this
and
number 4PQ, right, where P and Q are odd prime numbers, then they can be factored into only these two ways, right? In E zone. So this is an E prime factorization, right?
right.
Right. So then what is the smallest what I can choose? So they are asking for the smallest number, right? So what will be the smallest such number?
The smallest. Well, but P and Q could be anything. How would you know which one is the smallest?
Yes. P and Q can be anything, but we are trying to get the smallest one, right? So what will be the smallest?
2PQ or 2P.
No. What values of P and Q will make this number n 4PQ to be the smallest one? So that is the question, right?
I mean, so from where you're going to get the smallest one?
No. The question you understood, right? What they are asking.
The smallest number that has two different factorization products of E primes. Smallest number. Find the smallest number.
Right.
Okay. But from where you're going to get that?
Yes. So we can choose the particular value of P and Q, right? So for example, if I choose P and Q both to be 3, so that is the smallest prime number I can choose, right? So n equals to 36 in that case. So 36 is the smallest number in the E zone that can be written as two different prime factorization. So one is 2 times 18 and another is 6 times 6. So this is the
Okay,
answer.
you're replacing P and Q with just any odd prime.
Yes. So since we want to find the smallest one, we will replace by the smallest odd prime we know, that is 3.
Okay, and the next one would be 4 and 3. No, but 4, but they must be prime, right? Then would be 3 and 5.
Yes, but we can take them both of them same, right? So that is not a problem. So that's why I took because if I take 5, then it will be bigger, right? But they want us the smallest number, so I take both of them to be 3. So it is.
Yeah, that's the first one, right? That's the
Yes.
first one. But then the next one, what would be the second one?
Second one is 3. Yes. Second one is 3 and 5. We can choose.
Oh, it only says the smallest one. Okay,
Oh
that's
yes,
to
they are
say
only
that.
asking the smallest one.
Okay.
Yes. Fine, right? Okay. So the next question means in the next same part they are asking one more question. That is 180 the smallest number with 3 factorizations. So now they are asking. So what will be the smallest number that has 3 different factorizations? So in general, when does a number has three different factorization in the E zone?
When a number has three factorizations, I mean, so 4PQ is like a generalization of all E primes, right?
Yes, yes. 4PQ is the generalization of all numbers that can be written into only two E prime factorization. That has exactly two E prime factorization. That is your 4PQ.
Right.
So now they're asking, what about the three factorizations? If I want three factorizations, then what is the smallest? So for 180, I know that it has three factorizations. So they are asking, is 180 the smallest one, or we can have even smaller number? So that has three factorization.
So PQ it's because it has two different factorizations. So we need
Yes,
one letter more, PQ and R.
yes, yes. So PQR. So for that we need eight PQR, right? Or four PQR will work. What is the idea?
I don't know.
Okay, let us
I
say.
mean, we need three letters, PQ and R, but
Right. So we need at least three prime factors. So if I take PQR, then how many factorization we can possible? So one is 2 times 2 PQR. So that is what that will work. Then we have 2P times 2PQR. Sorry, 2QR, right?
mm-hmm.
Then we can change it. So for example, we can have 2Q times 2PR, right?
Mm-hmm. Right.
And we have 2R times 2PQ.
Mm-hmm.
1 minute. So 2PQ we have, right? Anything else is not possible. These are the four things possible, right? But the thing is, they're asking three factorization. So how to manage that? So they are not asking four factorizations.
But you could have there also QR multiply 4P.
No, no, that will not work, right? Because so what you are doing is QR times 4P, right? But
Yes,
then
but
QR is an odd number, right? So that does not belongs to the ism. So we have to make all the number even numbers, right? So this will not work.
so you need an odd number. Sorry, you need an even number.
Right, right. Because factorization means every number that should belong to the E zone, right?
Oh, okay, okay,
So that
okay,
will not
okay.
work. So here actually PQ are odd primes.
But if we
So
add 8, we will have more combinations, right?
yes, tell again.
If we add R,
Yes, yes.
sorry, if we replace 8,
8.
if we put 8, we will have more
Yes,
combinations.
yes, 8. There will have more combination, but we want three combinations. So this will
Mm-hmm.
also not work, right? Because this has four combinations, right?
Right.
So how to reduce it? So any idea? But we also saw that
Um,
4PQ will also not work because that has only two factorizations. So
if we use 6,
no, 6 because it has to be divisible by 4, right? Otherwise, if it is not divisible by 4, then it is itself a E prime, right?
if it is not divisible by 4, we cannot say it is an E prime.
Yes, yes, it is an E prime, right? If it is not divisible by 4, so that will not work. So what we can do is slight change. So the slight change is if P and Q are same, right? If the two prime factors are same, so then what is happening is, so this is nothing but 4P square R. So it is P and Q are not distinct. Okay.
Mm-hmm.
So if P and Q are not distinct, so then these two factorizations are same. Check. Because
Right.
P and Q are not distinct, then these two factorizations are same. And then the total number of distinct factorization is reduced to 3. Right?
P and Q.
So this will now change into 2 into 2p square r, then 2p into 2pr, and 2r into 2p square. So this will be my 3 factorization when P and Q are same.
Right.
So now, so P and Q are same, and R is and they are not equal to R. So R has to be distinct. So then, what is the smallest number we can choose?
3, right? 3, 3.
Yes, yes. P and Q we can choose 3. What is R?
5.
Right. So next prime, the next odd prime is 5. So what you can choose is P equals to 3, Q is also 3, and R is 5. So then, what is the number?
39, 45, 19, 180.
Right. So yes. So indeed, 180 is the smallest number, such that it can be written into your 3 prime factorization, right?
Yeah, so all the combinations give the same 180, right?
Right, 180 is the smallest number, and if all of them are distinct, means so if you want four prime factorizations, so means like this, then all PQR has to be distinct, right? So then the smallest number is P equals to 3, Q equals to 5, and R equals to 7, right?
That would be the next one.
Yes, yes. No, this one will be the smallest if all of them are distinct, right?
If all of them are distinct, yes.
Right. So that will be, then the number will be, so 4 times 3 times 5 times 7. How much is that? I think that is 420, right?
Yeah.
So 420 is the smallest number, such that it can be written as product of 4. So that is what they're asking the next question, right? Find the smallest number with 4 factorizations.
Sorry, the reason why you choose 4 is because when e number divided by 4. So I mean, before we say if an e number is divided by 2, and the result is odd,
Yes, then it is an E prime.
then it's in E prime. But
Right.
if we divide by 4,
Yes.
and the result is an odd, because 180 divided by 4, the result is an odd number.
Yes, yes.
Then we say the 180 is not an E prime.
Yes, yes. Then it is not an E prime, right? Because we have a E prime factorization, right? So for example,
Okay,
180, we already know, right? So it is 18 into 10, right? So both are E prime, right? Fine.
Right, that's why 180 is not an E prime. It
Right.
is
180 is not an E prime.
even.
Yes.
Okay.
Okay. So today we'll stop here then.